Moving on to section 10.4, and we're going to introduce a new type of angle. So you guys already know about central angles and that they're at the center of the circle. We're going to be adding on to called something an inscribed angle, which the part that says in gives you an idea that it's still inside the circle, but it's not going to be at the center. Okay, so an inscribed angle is an angle with a vertex on the circle and sides that contain chords of the circle. Okay, so I got to show you what this looks like. So over to the side, you're going to draw a circle. You're going to put the vertex on the circle instead of being at the center, and then you're going to make two chords. That is an inscribed angle. So let's say my inscribed angle is 20 degrees. That does not mean that my arc is 20 degrees because it's not at the center anymore, so they don't match. We're going to actually look at a theorem that shows that the arc is twice as big as the central angle because the central angle is pulled way back on the circle. So keep in mind it's not equal anymore, it's half. The angle is half the arc. And then I'm going to introduce this new term called intercepted arc. So I want you to think of an intercepted arc like an interception in football, if you've ever watched football, where a pass is like cut off from the other team. An intercepted arc is like an intercepted pass. It's like literally cut off from the rest of the circle. Okay, so I'm not going to fill in the definition. I'm just going to show you what it is, and then you guys can go back. Well, maybe I will in a second. All right, let's see. Let's draw an inscribed angle, and then I'm going to label this arc AB. That arc AB is called an intercepted arc because it's on the inside of that inscribed angle. It's cut off from the rest of the circle. So over here it says an arc that has endpoints on the sides of the inscribed angle, and it also lies in the interior of that inscribed angle. So think of it as like an interception in football. It's the same idea. It's a cutoff arc from the rest of the circle. It's inside that inscribed angle. All right, so in a normal time, we would take the time to do this investigation, but I'm just going to go through this inscribed angle theorem down here and skip that investigation for now to save time. So if an angle is inscribed in a circle and the sides are chords, then the measure of the angle equals 1/2 of the measure of the intercepted arc. So we just talked about this. So let's say that my intercepted arc was 50 degrees. That would make this inscribed angle 25 degrees. Now, if I add a central angle in here, you're going to notice that that central angle would still be 50 degrees, but when it's pulled back and on the circle, then it becomes half. So now you just have to remember there are two types. There's a central angle and there's an inscribed angle. All right, and there are three ways that this can happen, but I'm just going to go over them with you in examples, so we're not going to fill in these bottom three cases. So let's go over and look at how this works. This is easy peasy. So when you guys have an inscribed angle that's on the circle, you look for the intercepted arc, and sometimes it does help to take the angle and extend it like out past the circle, like its arms going out. This is called the intercepted arc, and that arc is going to be twice as big as the inscribed angle. So if the inscribed angle is 36, all you're going to do is you're going to do 36 times 2, and you're going to get the intercepted arc as 72 degrees, which is the arc they asked you to find, the measure of AC. And again, that's measure, so it's degrees. Okay, so let's go over here. This one is the opposite. This time they gave you the intercepted arc, and you're asked to find the inscribed angle. You just do 62 divided by 2, and you're going to get angle N is 31. So this answer is 31 degrees. And finally, QPR. Okay, this is the major arc that starts at Q and goes from P and ends at R. Well, it's not so major. I guess they use 3 letters on a minor. Okay, so that is the arc down here. So what's going to happen is we're going to take our central angle. I lost my red pen. I'll just use this one. Okay, we're going to take our, not central, inscribed angle. We're going to take the inscribed angle. We're going to double that to get this arc right here. So what's going to happen is I'm going to take 113 times 2. That's going to give me this 226 for this intercepted arc. Now, if that's 226, then if I would like to find QPR, which is down here, then I'm going to finish by just taking 360 and minusing off that 226. So that one has a little bit of an extra step. So you're going to get 134 degrees for the arc that's underneath that, at the bottom of that circle. Okay. So now that's going to move us to a different theorem, a second theorem. So these are all going to have to do with inscribed angles. Okay, so let me briefly show you this theorem, and this one's pretty easy to use. So this says if two inscribed angles intercept the same arc, then the angles are congruent. Okay, check this out. Take angle C and extend it out past the circle. So like take the arms of the angle and go out past the circle. Now take angle B and extend it out past the circle. You might notice that they both intercept this arc DA. So if these two angles both intercept the same arc, it makes the two angles congruent. For instance, let's say that this arc was 100, then both of these angles would both have to be 50 degrees because they're inscribed and they're both half of the arc that they cut off. But they match because they cut off the same arc. Okay, so we're going to skip down to this U try, and you're going to go back in a minute and try these that we skipped, but we're going to go down and do one together. So on the U try, it says, what arc do both A and D intercept? So let's look at angle A. So if I extend angle A out, it intercepts arc BC. So we put BC with an arc mark. That makes angle A, and if I do the same thing to angle D intercepts that same arc. That makes these angles congruent to each other. Okay, so what that means is A is going to have to match D. So if A matches D, in order to find the measure of angle A, I can set these angles equal to each other. 6y minus 2 has to equal 5y plus 8. And now I'm going to solve for y. So y is going to end up being 10. And then it asks for angle A, so I'm going to plug that back into 6 times 10 minus 2, because that's angle A. And I'm going to get the measure of angle A equals 58. So it's a little algebra there. Okay, so now let's look at this other one. It says, what arc do both B and C intercept? Okay, so let's look on the other side of the triangle. Let's extend angle B, and let's extend angle C. They both intercept this arc right here, arc AD. That means those two angles will be congruent. So I'm going to set up the equation. We're not going to solve it, but we know that B and C would have to match each other then because they both intercept the same arc. So you would set 6x minus 3 equal to 7x minus 11, and you would solve. Okay, I'm just going to give you what that answer would be if you solved. And then if you plug back into angle C, you will get 45. So that's just using algebra again. But the point is, as long as the angles intercept the same arc, those inscribed angles will be congruent to each other. And vice versa. You can do it both ways. Okay, so that's the first theorem. So flip it over. Again, there's another investigation. So if you're kind of curious how these work, these investigations will show you how they work. But I'm going to go down to the theorem itself, and I'm going to read you the next theorem. So this next theorem says an angle that is inscribed intercepts, if it intercepts a diameter, then it will be a right angle. So an inscribed angle that intercepts the diameter is a right angle. Okay, so come over here. This is an inscribed angle, and it's going to intercept a semicircle. So let me show you where that semicircle would be. That's the arc that it's cutting off. So if you extend that angle, it cuts off this. This angle, or this arc, is 180 degrees. So that means this central angle has to be 90. So that's what that whole theorem is. If you have an angle that cuts off a semicircle, then that angle will be a 90-degree angle. All right, so I'm going to show you an example of this one. So on this question, it wants to know what x is. Okay, so let's look. If you guys will look at angle y and extend it out, angle y cuts off this semicircle right here. That semicircle is 180, and since angle y is an inscribed angle, that's going to make it 90. Okay, so if angle y is 90 and I want to find x, then what I can do is say, well, I know that my triangle needs to add up to 180. So I'm going to do x plus 12 plus x plus 90 equals 180. And that's going to help me get the x that I need for that question. Okay, so if you solve that and use your algebra, you're going to get x equals 39 for that. Now, they want to know what w is. Okay, well, great. I know x is 39, and w is, angle w is x plus 12. So I'm going to just take that 39, and I'm going to add 12. And so the measure of angle w will be 51. So again, I'm using the fact that I have a right angle in there. That's a right triangle, and I'm adding them all up to 180. Okay, you'll go back and try this try after the video. And there's one last theorem. And again, if you're curious where it comes from, feel free to go back and do the investigation. It's going to kind of show you where this comes from, but I'm going to show you the theorem. All right, last theorem. If a quadrilateral is inscribed in a circle, then opposite angles are supplementary. Okay, I'm going to highlight. I want you to highlight, star, cloud, whatever you want to, that word supplementary. Because most kids think they're congruent, but they're not. They're supplementary. All right, so let me show you an example of this. So we're just going to look at 12 and 13. This is a quadrilateral inscribed in a circle. And notice it's inscribed because all the points are on the circle. Okay, opposite angles are supplementary. So I'm going to first find angle R. Okay, well, angle R is 3x, and I know 3x plus 75 has to equal 180. How do I know that? Because in this theorem, we said opposite angles are supplementary. Okay, when I solve that, I'm going to end up getting x equals 35. Now, it wants the measure of angle R, so I'm going to plug that back in. So the measure of angle R equals 3 times 35. So the measure of angle R will be 105. Again, I used opposite angles are supplementary. Not congruent, but supplementary. Okay, last one. I want to find S. Well, S is supplementary with Q because it's an inscribed quadrilateral. So 2x plus 110 equals 180. Again, I solve for x. X is 35. And then I'm going to take that 35. Well, that's a coincidence. Oh, well, you know what? They were the same letters. I guess I already knew x was 35. I was thinking this was a y. So I didn't even have to do that. I knew x was 35. But then I'm going to put that back in. So the measure of angle S is 2 times 35. And the measure of angle S is 70. Opposite angles are supplementary and then not congruent. That happens all the time. Kids think they're congruent. That's only if it's a parallelogram are opposite angles congruent, but these aren't parallelograms necessarily. Okay, so you're going to go back through and finish the ones that we skipped just to have that extra practice before you would try to go on.